Okay, now this is one of my many favorite topics here because it's a homegrown method, and once again, oops, wrong button. The delta 5 method. The delta 5 which you measure here. I told you that we use this method for determining the crack extension resistance as a function of crack extension. We don't need any calibration functions, no finite element stuff before. We just measure a displacement at a selected point, full stop. It's that easy. When you do J integrals, you have to have calibration functions and so on and so forth. It's that easy. And what comes on top of that, you can use it on any structural component. When you have a structural component, for example, a pressure vessel or whatever, and you can afford, with a crack, you can afford an on-load and unload condition, you measure the delta 5 as the crack driving force, just as a displacement. Nothing else. No calibration function, nothing. It can't be done in every case, of course, but in principle you can do it this way. And so, like I said here, you can do it in all configurations, including structural components. We did tests on little pressure vessels, and it worked beautifully. That's what I just said. Under load and unload conditions, you can measure it as a crack driving force. Just measure displacement. This is the crack driving force. Now, from that we almost a quarter past one here. We expanded the method and created something that you have already seen, which we call the engineering treatment model, or as an acronym ETM. And we describe or estimate the J integral and the CTOD in the form of delta 5. And I've shown you, okay, so the same method can be used for driving force and resistance, so we can handle both sides of the equation with ease. Now, once again, just running quickly through it, you see the crack driving force is proportional to the force with this relatively high exponent. You see it's a relatively flat curve here. Whereas the J integral has an additional n here, so for the J integral the curve would be a bit higher because J integral is an energy integral, and energy is always force times displacement, you know, force times the path. And so the force comes on top of it, and that's why we have this 1 plus n here. Once again, everything is normalized, and the normalization gives us a description of the crack driving force independent of size and geometry of the component. So that's why we call it master curve. Now, a few examples for validation. Here we had tests, biaxial tests with different biaxial ratios. Here it's fully biaxial in the sense that both forces here are the same, and you see it's a relatively thin section, and with these dimensions here. And in our lab we have a 3D test machine. You can apply biaxial loads, plus we have a second set of actuators, so the machine has 6 actuators, which was specially designed for us. So it was not able to buy it from stock, off the shelf. And I can tell you it caused a lot of headache to the producer, because the problem wasn't the hardware. The thin company Schenck in Germany was very well known for very good mechanical parts of the mechanical part of testing machines, but they had trouble with the software. And why? You should imagine, in order to have a good and appropriate loading condition, the 3 loading axes have to meet in a point, which is not a mathematical point, it's a plus minus, whatever it is, but we gave very strict requirements, and that was the problem, you know, to control the 6 actuators such that the limit will not be exceeded. So that was, had a delay of 2 years. That was really, but it's a fine equipment. So here we did biaxial tests. And these are the test data, force versus Craig extension. So really, it's not the R curve as such, but it's just the applied force. And here, what do we have here? Forget about the SYNTAP here. Level 3 is our ETM. The SYNTAP is a European procedure. And level 3 here, it's the red curve, which is the ETM. You see, in my view, it's kind of okay. We compared the number of tests. Some of them had inclined cracks, so it was a mixed mode testing, mode 1, mode 2. And so, like before lunch, I gave you a similar diagram. It's predicted maximum force versus experimental maximum force using the ETM, and this is a plus minus 10% deviation that you see. In my view, it is kind of okay. So it's 2 different aluminum alloys. These were data from DLR, the German Aerospace Research Establishment. Now, this was an interesting exercise. This is the cross-section of a pipe. The diameter was 700 millimeters, and it was an obsidian stainless steel. Tests were done. These tests were done at the then company, it doesn't exist anymore, Interatom, and they worked on a German breeder program. Fortunately, this program became never effective and heavily against nuclear energy. And, but the tests were very interesting. These were pipes. Some cases the shear pipes were tested. In other cases, welded pipes were tested with butt welds with a crack in it. And at that time, I did the analysis. At that time, I didn't know anything about mismatch, fortunately, and I made the mistakes that I ignored the effect of mismatch. But the fortunate thing is the remaining ligament was so long, as you can see here, you know, that I couldn't make any mistakes. So it was quite fortunate. And just to let you know the background, at that time it was 1988. I spent about 10 days in the hospital, and I had a room for myself. And once the pains had gone, I asked my wife to bring me my work equipment, so from calculator, millimeter paper, did everything by hand at that time, millimeter paper, ruler, and so on and so forth. And it's a complete analysis in the hospital. And the doctor sometimes, if you're crazy, said, no, this is the most quiet environment you can have to work in a very relaxed manner. You get food 4 times a day. And sometimes a nice nurse comes in, you know, and the doctor comes, how are you, and so on and so forth. So I really enjoyed it, and I can only recommend that. But it works only when you have a room for your own, and when you don't have pains. So the pains had gone, and it was just wonderful. Yeah, I did that several times later too. This is interesting so far. You see, for every experiment, I did more than one analysis, several analyses here. Why did I do that? For one analysis, I used the nominal data, nominal value for thickness, nominal value for diameter, nominal value for yield strength, And then I got some data sheets from the company who did the tests. And then it turned out that each pipe had different values of whatever. The thickness was, nominal thickness was 11 millimeters, and here it varied actually between 10 and 14, which does a lot to the end result. The diameter was not too bad, but did the analysis with and without pipe ovalization, because when you bend a pipe, it ovalizes a bit, or it may overlie, so you did with and without. You saw it's quite a bit of work. You do the R-curve analysis, you have the R-curve on your millimeter paper, and you have to vary the applied bending force, and you overshoot, you undershoot, and in the end you do an interpolation. So it was quite tricky, but remember what I said on Monday, it is never wasted time when you do these things by hand, because while you draw your diagrams, you start already thinking, why is it this way, why is it that way? And I can only recommend that, but you will never listen, will never accept that, I know, but I'm saying it. Okay, you see, there is substantial difference here, and remember what I said on Monday, I think it was Monday or yesterday, whenever you have to do an analysis, a failure analysis, look at the broken parts. Don't believe what people put on your desk. I mean, there are many cases where you have to believe. You can't go to an offshore platform and measure the thickness of whatever it is, you know. But you have to be extremely careful, otherwise you can come to false conclusions. Now you have already seen this once again here, the R-curve analysis. The same picture as yesterday, so all these tools come more or less to the same result. And again, this is the Airbus panel. I don't show the photo again. This is a sketch of that panel, and here you see the stiffness, and yeah, the setup here, and once again here the various stress strain curves of all these nasty details. Yeah, here is you see the dimensions of the shell, about 2 by 4 meters, and this was we did the analysis twice. Number one, using the cohesive model, what I showed you previously, and here we did the R-curve analysis. I mean, it was Cornick and one of his colleagues, and here is again the experimental maximum load in terms of internal pressure. And the first calculation, first analysis, overshot a little bit the real failure value, and so it was on the non-conservative side. But then Alfred, he's a very picky man, you know. Not always easy to deal with, but he's very picky and reliable. When he tells you something, you can really swear, raise your hand. So he went down in the cellar because we had the broken part in our cellar, and investigated the environment of the crack tips, and he saw that one of the rivets here had failed during the test. So the rivet, of course, is supposed to carry a part of the load, but in that case, at a certain moment, the rivet broke and didn't carry load anymore. So this was, of course, not included in the first analysis. And then he sat down. I mean, it took years to do this analysis. You can't believe me. It's not just you sit down and do it within 2 weeks. And so he found the broken rivet, did the same analysis again without the rivet. And you see what happened here. This is the drop by the broken rivet, and just that's here we go. And there was a further thing that I did not include here. I mentioned yesterday that there was a special pre-cracking procedure, especially insofar as very high load cycles had to be used, and we heard about that only afterwards, after all the work had been done. You know, we didn't get the information. Like we say in Germany, you had to pull every worm out of people's nose, you know, to get to the. It was difficult, and it turned out that the pre-cracking load was almost 90%, which is, you know, normally not acceptable, but here in this case it's okay. But this pre-cracking, at this high pre-cracking load, should have had an effect on the result. And indeed, believe it or not, Alfred sat down and did a further run, but with just one load cycle, which, because the whole thing is quite time-consuming, with one previous load cycle, and this had a visible effect again on the final load. So again, get as much information as possible. Fine. Now I'm coming to a different point, which has nothing to do with lightweight structures, but it shows you an important lesson that we had to learn, and it can happen everywhere, not just in lightweight structures. Years ago, we had a relatively large EU project called BIMET, Bimetallic Weld. You see the time frame here, and it was part of the European Nuclear Fission Safety Program. And here you see the project partners are quite some institutes and electricity de France and Framatome, and the others were research centers. And it was a very, very good collaboration, very good European. That's why I like all these European projects and working groups. We get in contact with people from all European countries, and which is very important. Now, Alfred Kornig again, we were responsible, we didn't do any tests, we were responsible for the analysis. So we organized the analysis, our own analysis and the analysis of other people. And here you see the test setup. The diameter here is 170 millimeters, relatively thick wall. And here we have a ferritic steel and austenitic steel. And these are just bending arms that don't contribute to what's happening here. And you see the weld, representative of nuclear pipings. And here was a crack. Unfortunately, it was only a saw crack. It was very thin, very thin, but it wasn't a fatigue crack. And two tests were done. Here's a close-up of the weld, the ferritic steel, the austenitic steel. Here you see the various weld layers, and heat affected zone on the ferritic side, a buttering layer, another buttering layer. So you can imagine that we had quite a variability of the tensile, these tensile parameters, plasticity parameters across the weld. And here you see the defect. And now here you see the miniature specimens that I showed you already yesterday. And Alfred tests. These are not standardized, of course, but he wanted to learn about the local variation of the stress-strain properties. And this can, of course, only be done using very small specimens, so that you can capture only really small volumes. And not everything is shown here. So it is this direction, he did tests in the longitudinal direction, and so on and so forth. So everything across the whole belt here. So it's dozens of tests. And these are the stress strain curves. The total stress strain curves here, just the it was cut off here to blow up this axis. And you see, this is the weld metal, the variability within the weld metal, top and down and left and right. And here are the various, doesn't make sense to go to the details here. You see which is a mismatch from 300 to 700, more than a factor of 2. So quite a challenge, because everybody was asked, everybody of the participants was asked to use his own assessment method, either finite element or purely analytical methods like we do or whatever, to learn about reality, real world, you know, how compare the various analytical results. And yeah, we'll see in a moment why I'm presenting this as an example here. And this is the result. I have to explain to you. On the vertical axis, we have the bending moment. Here, the crack initiation measurement was done using the electrical potential method. Very, very good experimentation. And so this was kind of the variability or uncertainty. And Alfred thought this is the representative value of about 150. And if you don't stop him, he gives you three digits behind the comma, which in the end doesn't make much sense. And here is the end moment, the end of test, which is 188 as compared to 154. And here are the various contributors, so GC, A, France, and GKSS, 2 GKSS, TWI, GKSS, Sisters, and so on and so forth. And this had to be predicted. What you see is almost a Milky Way. The left-hand side are EAM, means the engineering assessment methods, like the ETM that I presented, like other ones. There are several around. And on the right-hand side here, we have the finite element analysis. And what you see here is a disaster. That shouldn't happen. This didn't let Alfred sit down and sit back and do nothing. He said, I must find out what's the reason. And the reason was so trivial, you won't believe it. Everything can be made wrongly. Full stop. Everything. The reason in the end was Alfred looked at the yield loads, the yield bending moments, and he saw this is not fracture mechanics, this is like Milky Way, such a scatter band. It must have something to do with the plastic deformation properties. You know what happened? The tensile tests, standard tensile tests, not the miniature tensile tests. The miniature tensile tests were done by Alfred afterwards. The standard tensile tests were done by one institution, VTT in Finland, and the data pairs, force versus, or stress versus strain, I don't remember, it doesn't matter. The data pairs were circulated among the participants. And every participant made a plot of the stress-strain curve and derived the RP 0.2, and it was there where the mistake was made. It's unbelievable, a standard task, determine the RP 0.2 of given stress-strain data points. Shouldn't happen. Now, the problems revealed when Alfred analyzed the data, and the yield strength from individual fits varied between 260 and 430 megapascals. That's why the yield moments were varying that much. And also individual formulas for the yield load were used, but this was allowed. And the result was substantial variations in yield load and hence in predicted failure loads. Really, I mean, this would not have been detected if we
had to acquire money for every hour we work. Alfred did the analysis long after the project was closed. We didn't get any money for that. So the result would have been, this is the scatter band of the predictions, full stop, which is totally unsatisfactory. So it was our own intention, we paid from our in-house money, and this on the background of the situation of some universities was really very valuable work, and we learned from that. Now, being more general again, because we are coming more or less to conclusion, we need reliable input data. For example, the applied loads, residual stresses, I mentioned that already, and then mass forces, thermal stresses, location of crack initiation, local stress peaks, and routine load history. And the quality of input information is important, and experience shows that input information is subject to uncertainty. And I've given you 3 examples. Crack detection, I think I haven't yes, that comes in a moment. Cracks comes in a moment this year. Structural dimensions, something that I told you during my presentation of the plaques that I analyzed, material data. And here's the interesting diagram which was obtained on railway axles. I don't think it's a fundamental information that we have here. Here's the crack size, and here's the probability of detection. Probability of detection. And 4 different techniques, ADR techniques were used: magnetic particles, eddy current, ultrasonics, high-level scan, and ultrasonics is the far-end scan. Far-end means you have an axle and you attach your transducers at the ends of the axle where the resolution, the overall resolution is relatively low, but when you walk along the shaft of the axle, then you have a better life. And this is shown here, 3 and 4. And what is depressing is that even a crack depth of 10 millimeters using the green technique here gives you only an 80% chance of finding the crack. There was a conference years ago having to do with crack detection probability in nuclear installations. And there was an interesting presentation about a finished EU program. And at the end of the presentation, I stood up and said, your presentation showed me that I still stick to my opinion that NDI is black magic. And it's really, in many cases, in particular when you have thick wall structures, difficult. Okay. Another point, this is crack propagation data, fatigue crack propagation data. Here you have the data points. Which ones do we use? Which ones do we use? To be on the safe side, you take an upper bound curve. Upper bound means you overestimate, on average, you overestimate the crack propagation rate, which means you do an underestimate of the remaining lifetime. And you ignore the threshold value, which gives you more safety. And now if you do text slides, all input informations are subject to scatter, for example, dimensions, yield strength, crack detection. That was, yeah. Once again, there is a schematic of crack size distribution. This is the crack size axis, and this is the number of cracks or defects. Very small defects below is the detection. Here's the detection limit, NDI, here's the detection limit. Everything that is left to this line here can't be seen. So very minute defects are always there. Think of the second phase inclusions, which you can regard as defects. Then defects introduced during fabrication, for example, weld cracks. Or when you form something out of a sheet, you can introduce defects. And from here on, you can see what's happening. And sometimes when you find a defect after production, you eliminate it by repair measures, and so on and so forth. You know, so this is makes sense to have a look at it when you do a crack analysis and so that you get a feel about what's happening. Now the final thing is something that I recommend to use. Again, the equation applied load, is it equal to resistance? And from the applied loads, I should say, forces, so on and so forth, plus the geometry, all the geometry's variables, we determine the local stresses. And from the local stresses, the stress intensity factor. And at the right-hand side, we have a host of material properties. I don't have to go into the details here. And everything as functions of the material batch. They scatter from variability from one batch to another one, from one heat to another one. Temperature, environment, loading rate. And from this you choose the appropriate material property, and then you have all the information together to do your analysis. That's it. Thank you. This in the Einstein year, you know. So this is, my skills are quite limited, you know. What I'd like to show you briefly. So again, within the frame of linear elastic fracture mechanics, because it's easier to show, we start with the stress intensity factor equation, sigma times del IA times the calibration function. And we have trouble with all these parameters. Stress intensity factor. You may remember that on Monday I told you that it is important here's a prediction, to have a look at the yield force, yield moment, or whatever it is, because you can't use linear elastic fracture mechanics beyond yield. What sometimes happens, and the bad news is that you are on the unsafe side. So you need to know the yield force here, which in a tensile panel is no problem, but when you have a complex system, you have to determine the yield force or moment or whatever it is. Please, you don't make this mistake. If you don't make the mistake, you have to pay a penalty. You have to give me 200 euros for the lack of success of this course here. And sigma, we have already dealt with this point in depth. So it's the applied forces, it's residual stresses, it's mass forces or inertia. And what else do we have? Thermal stresses. When we have coatings, in many cases when we have coatings we have residual stresses. Unfortunately, sometimes they are positive, which can be very bad. The equation was not complete here, sorry. The failure condition is given by the equality with the critical stress intensity factor of fracture toughness. Then y of A over W. We have to know where the crack is going to start. I remember experiments done by the predecessor of ELDS when they designed the what was then the Eurofighter. They had a tensile member and a bolt here. So it was loaded this way. The bolt, of course, had a little bit of clearance. And it took a series of experiments to learn where the crack was going to initiate. It could have initiated here, it could have initiated here, 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 depending on the clearance, most probably also depending on the material pairs. The location has a strong effect on the magnitude of our Y function. Kc or K1c, whatever. If you have a material with variable yield strength or maximum strength, tensile strength, and here we plot the critical K value, and we get this relationship. The harder the material, the lower the toughness normally, you know. You can increase the toughness by adding alloy elements, but then you have a different material. You have high strength and high toughness, but you have to pay for it, like I said several times, you have to pay for it in terms of more expensive material. And sometimes when you have age-hardened materials, the relationship, the correlation between toughness and strength can be unequivocal, because you can get a curve like this here. And this is due to overaging. What happens? When you overage, you soften the material, so you would expect that the toughness goes down again. No, it doesn't, because when you overage, you generate precipitates of the equilibrium phase, relatively big particles, and many of them are precipitated at great boundaries. So you have a relatively dense chains of particles which give you a fracture path of low energy. Then when we deal with polyolithic steels, as a function of temperature, here we have very big steels. You get something like this here. We have to take care of the operation temperature. It should be, it has to be above the transition temperature. And this is not enough. We have substantial scatter, as I showed you yesterday, by an order of magnitude. And there's no way to avoid statistical treatment of the data and later of the analysis when you go to the structural component. But the point is also that with these steels, the transition here is affected by the loading rate. So when you have a high loading rate, the steel embrittles and it shifts the transition curve simple K dot, so loading rate. It shifts the transition to higher temperatures. And you may ask, so what is it good for? Well, it is probably not the core item of lightweight structures, but it is always good to look left and right. Think of an offshore platform, and it's winter, and you have a barge that has to deliver something to the platform, and a big wave comes and smashes the ship against the leg of the platform, which can be a relatively high loading rate, but which is unknown. You don't know how the stress is spread all over the place, so it is a point to be looked at. A further point, you have a rolled plate, maybe aluminum. Get back to lightweight structures. And you have at least 6 different orientations, and in these different orientations, we have done all this in detail. You have substantially, sometimes substantially different toughness values. It is due to the microstructure, due to the rolling process, the microstructure is aligned in the rolling plane and in the rolling direction. So it matters if your crack is, for example, is located here. So the crack propagation direction is this way, or it's located here. Crack propagation direction is this way, or you have your crack lying in the rolling plane. You have 2 different directions. The difference can be substantial. So this is the worst here. Pulling perpendicular to the rolling plane is almost fatal. And this is why, for example, coming back to offshore, why there is a requirement for offshore steels to have very low sulfur contents, because the sulfur creates the manganese sulfides, and they're quite big particles. And in some cases, you have designs with a plate and something welded on, and if this carries a load perpendicular to the plate, then the crack lies here, and you can have total delamination of the plate. So. Okay, something similar, I'm not giving you a drawing, something similar happens to cast and forged materials. Within one piece you can have different thicknesses, and the different thicknesses have different toughness values, you have different orientations, so it is a nightmare, you know. And you can't just characterize the material and say this is a critical K or J value of steel XYZ. This is rubbish. You have to give more details, temperature zone is natural, but also crack orientations, and yeah, once again, when you have a cast material a component or a forged component, it is, you have to be very, very careful with that. So this should be enough for the material properties. The final thing is the crack size. No fracture mechanics without a crack. For example, you have a thick section and welded, maybe. You have a crack which has a 3-dimensional nature, a 3-dimensional plane lying somehow and somewhere, and your ultrasonics inspection gives you just a projection of the crack. I mean, you shouldn't be interested in the exact shape of the thing. What you need is a projection onto that plane that is perpendicular to the maximum stress. Okay, so you have something quite irregular, and you do the projection onto the plane of maximum stress or lowest toughness or whatever, and then I think you can get along with it. The probability of detection was already mentioned a few minutes ago, and coming back to the aeroplane crash that I showed you at the beginning, the comet. So if this is the fuselage, and here was a pilot's window, and I'm magnifying this here. And in one of the corners, I don't know which one, a crack initiated, and during loading, and the crack became critical before there was a chance to detect it, and 2 planes were lost. They broke, the fuselages broke in cruising altitude, and the reason was, what people told me, I hope that it's correct, that they did not remove the plastic liners here around the window. And the crack became critical before it had left this liner. And the Lusaka crash that I also mentioned was an aeroplane where here the balancer broke, so the whole thing went nose down. Fortunately, it was only a freight plane, so there were no passengers on the plane, but the crew died, of course. And here in that case, the crack initiated in a piece of a built component, and it was not accessible to inspection. So already at the design stage, one has to be careful, whenever you know there are high stresses and whatever kind of conditions, including corrosion maybe, you have to take care of that and think of the accessibility of the critical locations. This is very important. And with these wise words, I would like to finish finally. Thank you again. Thank you very much.